Welcome back to Logic, Language and Information 2, and to this, the third in a series of lessons on mathematics and logic. Today's task is to think about the distance between real numbers. To begin, the distance between two real numbers, x and y, is the length of the line segment connecting x and y. We can express this algebraically as follows. When x is less than y, the distance is the number y minus x. If x is identical to y, the distance is 0, and if y is less than x, then the distance is x minus y. Now, we are not using functions, but that won't be a problem because what we really need is a bound or estimate on the distance between two real numbers. We're going to use a three-place predicate, d, x, y, epsilon, to mean that the distance between x and y is strictly less than epsilon. Now, we are not using functions, but that won't be a problem because what we really need is a bound or estimate on the distance between two numbers. We will use a three-place predicate, d, x, y, epsilon, to mean that x and y is strictly less than epsilon. This three-place predicate d is easily defined using the three cases. dx, y, epsilon holds exactly when x is less than y and y is less than x plus epsilon, or when x is identical to y and then y epsilon can be any positive number, or when y is less than x and x is less than y plus epsilon. In each case, the difference between x and y is bounded by epsilon. Here's a bunch of atomic formulas or their negations built with the d predicate that are true. We have not d 17, 13, 4 because the distance between 17 and 13 is exactly 4. But if we replace 4 by 4.1 or even 4.0000, as many as you like, 1, or any number greater than 4, we will get a true positive atomic formula. We get not d minus 9, 12, 20 because the distance between minus 9 and 12 is exactly 21, while d minus 9, 12, 22 is true. All that is needed for truth is that the third number for epsilon is larger than the actual distance between the first two numbers, x and y. Now, we can start building up a list of properties of the three-place distance predicate expressed as formulas of predicate logic. To begin, formula Roman 1 expresses that whenever dx, y, epsilon is true, then we in fact must have epsilon greater than 0 because the actual distance between x and y is always a number 0 or greater. The next formula expresses that for all x and y, there is a number delta that is the actual distance between x and y, and this is shown by the fact that dx, y, epsilon is true whenever epsilon is greater than this delta, and not dx, y, alpha is true for all alpha less than or equal to this delta. Formula Roman 3 expresses that for all x and y, x is identical to y if and only if dx, y, epsilon is true for all epsilon greater than 0. Paraphrased, the distance is less than every positive number, epsilon, exactly when the two numbers are identical. Formula Roman 4 expresses the symmetry in the x and y arguments, while Formula Roman 5 expresses what is known as the triangle property for distance. If dx, y, epsilon and dy, z, delta, then we know we can get from x to z via y, and thus conclude that dx, z, alpha holds whenever the third parameter alpha is greater than the sum of epsilon and delta. Formula Roman 6 expresses that the d predicate is monotone in its third argument. if dxy epsilon and delta is greater than epsilon, then dxy delta is also true. There are more properties of this distance is less than predicate, and you're going to see some of them in the online quizzes. Looking again at the definition of the distance is less than predicate, we can see that it is an equivalent formulation. There is an equivalent formulation using the difference between x and y, which is always the greater of y minus x and x minus y. Now, our first basic skill is to be able to read and interpret predicate logic formulas containing this new predicate d. The first one, for all x and y, it is not the case that dxy0. So, which of these sentences of mathematical English best capture its meaning? A, distance between any two reals is greater than 0. B, the distance between any two reals is never less than 0. Or C, the distance between any two reals is never equal to 0. In this case, the answer is B, because dxy0 means the distance between x and y is strictly less than 0. And in fact, this is never the case. To make sure you're clear about the meaning of this formula, now try assessing its truth in the standard model of the real numbers. The first option is A. The formula is true because for any choice of real numbers, x as A and y as B, if dAB0 was true, then since dAB epsilon implies epsilon is greater than 0, we would end up concluding 0 is greater than 0, which is a contradiction. So dAB0 must be false. The second assessment comes to the conclusion B, the formula is false because if we take x as 1 and y as 1, the atomic formula D110 is true, so not D11 is false. In this case, the option B is definitely wrong because, in fact, D110 is false. So the correct option is definitely A. Now an exercise for you. The previous one was an example. Consider the formula that says, for all reals x, y and epsilon, if the distance between x and y is less than epsilon, then y minus x is strictly between 0 and epsilon. So which of these three different assessments of truth is correct? Make sure you read them carefully. Okay, how did you go? For exercise 1, the correct answer is B. The formula is false because we can take as an instance x greater than y, such as x is 2 and y is 1. Then their actual distance is 1 and 2 is bigger. So we can take epsilon as 2 and get a true atomic formula, D212. But this instance of the consequent is false because y minus x is 1 minus 2, which is minus 1, and 0 is definitely not less than minus 1. As usual, if you have any comments or questions, look first at the course notes and then go to the discussion boards and I'll follow up there. Another exercise. Consider a similar formula which adds an extra conjunct in the antecedent of the conditional. It says that for all reals x, y and epsilon, if the distance between x and y is less than epsilon and x is less than y, then y minus x is strictly between 0 and epsilon. Which of these three different assessments of truth is correct? So how was that one? The correct answer for this exercise is C. The formula is true because from the definition of the predicate D, for any choice of reals, x is A and y is B, and for all epsilon, the following conditional is true. If dAB epsilon and A is less than B, then B minus A lies strictly between 0 and epsilon. Now we want to relate the distance is less than predicate to densely ordered and discretely ordered sets defined by one-place predicates. The first result is that if a p-set is densely ordered and the set has at least two elements, then it satisfies a certain distance denseness property. Now, this distance denseness property in the consequent of the above conditional says the following. For all numbers x in P and all epsilon greater than 0, no matter how small an epsilon, there exists a number z in the P set whose distance from x is less than epsilon. Paraphrased, this says, given any number x in P, we can find numbers z in P that are arbitrarily close as you want to x. Now, this conditional can be fully formalised in predicate logic, as shown, and it is true in the standard model of the reals. To see why it is true, suppose the P set is densely ordered and has at least two numbers in it. Then let A and E be any real numbers, and suppose A is in the P set and E is greater than 0, positive. We want to show that the formula, there exists Z, PZ and DAZE is true. The idea is to start with another number B in the P set such that A is less than B, or B is less than A in the case that it happens that A is the largest number in the P set. And from that B, keep on searching through numbers C in the P set such that C lies between A and B, and these numbers C are guaranteed by the dense ordering property. We keep on searching until we find a number C such that DACE is true. Okay, so in fact we can do a bit better and get a stronger conditional with the consequent is a biconditional. So now the formula says if the P set has at least two numbers in it, that's the antecedent, then it is densely ordered if and only if it has this distance denseness property. So it's natural to ask, well, is there a corresponding distance discreteness property? Well, a good candidate is that expressed by the second formula displayed, saying there is a number delta greater than 0 such that any two numbers in the P set are at least distance delta apart. So we might consider the condition if a P set is discretely ordered, then the P set has this distance discreteness property. Well, this seems plausible if we think of discretely ordered sets as like the natural numbers or integer multiples of 5, but it is in fact false. Recall exercise 2 in the previous lesson 5.2 where we looked at the P set such that Px holds if and only if there is a natural number n such that n is greater than 0 and x is equal to 1 plus 1 on n. We say that this, as we saw, this set is discretely ordered because there are no numbers in the P set that lie between 1 plus 1 on n and the next largest 1 plus 1 on n minus 1. But for this P set, we cannot find a positive distance delta such that any two numbers in the set are at least distance delta apart. This is because the numbers in the set get closer and closer to 1 and so closer and closer to each other. You can see the reasoning written out. If we did have a candidate positive delta, then we could easily be shown to fail by choosing a large enough natural number n so that 1 over n is less than delta. Then 1 plus 1 over n and 1 plus 1 over n plus 1 are two different numbers in the P set such that DAB delta is true and so not DAB delta is false. It is in fact the converse conditional that expresses a true relationship. If a P set has this distance discreteness property, then it will be discretely ordered, but not the other way round. This brings us to the end of this lesson on distance predicates in the real numbers. In the next lesson, we'll start looking at sequences of real numbers. So see you then.